Okay, our last example will be a little bit simpler than the previous example. This is the last example in section 321, continuity of a function. Well, we have a function whose domain is the closed interval from negative 10 to 10 into R, the real numbers, and it's defined as follows. This is a rational expression. It's got a fraction in it here. So this is defined everywhere except at negative 4, which we put a 0 in the denominator. So as long as x is not negative 4, it's equal to this expression. And then it's equal to negative 24 in the single case where x is negative 4. And we're going to prove that it is continuous at x equals negative 4. So this will just take a few sentences. If x is not equal to negative 4, then f of x is equal to, I think I'm going to factor it out and see what happens. Factor the top, and we would get 3 times x squared minus 16 over x plus 4, which is 3 times x minus 4 times x plus 4, because that's a difference of two perfect squares, over x plus 4, and we get 3 times x minus 4, which I'll multiply out. 3x minus 12. So this is exactly equal to 3x minus 12 for all real numbers except where x is equal to negative 4. I mean, yeah. All right. We know, I guess, from previous work that f of x has a limit at x equals negative 4. We've seen that in the previous chapter. Because remember, the limit does not mean that the function exists at, doesn't require that the function exists at negative 4. So either using sequences or delta epsilon proof, we know that the limit as x goes to negative 4 of f of x is equal to negative 24. Again, this doesn't imply that the function exists at negative 4, although we do know it does here. And we'll finish it up by saying that since this second line says that f of negative 4 is equal to negative 24, we apply theorem 3.1 and see that f is continuous. And basically, if you were to, since this looks like, let's see, 3x minus 12, we're done with the problem, but just if we were graphing this part of the function, let's see, it simplifies to 3x minus 12. Well, so the line looks something like this. It's got a slope of 3, a y-intercept of negative 12. But it is not defined at negative 4. Goodness, I didn't. All right, so there's a hole in the graph somewhere down here. But this exactly fills it in. This is saying that f of negative 4 is negative 24. So essentially, f of x is equal to 3x minus 12 for all x. Maybe if we'd have written that instantly, we would have not had to go through all of this work. It's simply a straight line. And it's simple to prove that straight lines don't not only have limits at every point, but that the limit is that the limit at x naught is just f of x naught.